Welcome to the Quality and Improvement section of the Royal Statistical Society and the KTH University workshop on the use of simulation to support modern day needs of manufacturing companies. Today, we've got the pleasure of having Erik Flores from the KTH University and Sweden and Dr. Jonathan Smyth-Renshaw of the QIS Royal Statistical Society. So the two of them will be taking us through the simulation of supply chains and production systems in driving operational excellence. In terms of agenda, we'll first start with Jonathan, who will take us through understanding variation and some basic statistics through the use of SPC. Jonathan will spend 30 minutes taking us through some materials, and then we'll have 15 minutes Q&A at the end. We will then break for 10 minutes. We'll come back at 10:10, and then we'll then hand over to Erik Flores, who will take us through an introduction to simulation. And he'll cover some concepts around simulation, why do we need it, and the benefits. And then he'll move into a session which is more of a hands-on practical session where he will show us the use of simulation within the Extensim software. We'll run until 11:55. We'll then break for 10 minutes, and then we'll have about 25 minutes after the break where we'll have a Q&A and discussion before we close. So just some housekeeping. The session will be recorded, but attendees can be deleted from the recording. If this is the case, please let us know after the event so we can remove any necessary details. In terms of cameras and keeping ourselves on mute, can you please keep cameras off and keep yourselves muted until we get to a Q&A time point. So I will be tracking questions in the chat, so please hold the questions to the Q&A slots and just capture them in the chat, and then I can feed them back to the presenters when we get to those Q&A slots. I'll keep an eye on the timings and the breaks. I'll just encourage everyone, please do come back promptly after we have the breaks, because there's quite a bit of content to cover, so I just want to make sure that everyone doesn't miss out any important details. Okay, so on that point, I'll just hand over to Jonathan to start and with introductions and get started.
There you go. Good morning. So yeah, I'm Dr. Jonathan Smyth-Renshaw, and as Omar's explained, I'm part of the Quality Improvement Group. And so this morning I'm going to show you 100 PowerPoint slides. No, I'm only joking. I'm going to take you through SPC and the use of SPC. So what I've done is I've prepared a presentation in Excel, which I'm going to go through. You can also see my camera. What I'm going to do is I'm going to talk about a technique, statistical process control. And when people do modeling, quite often they focus on the average, and obviously if you focus too much on the average, you just become average. So another important component of modeling is to understand the variation. So we're going to go through a technique which I think some of you have already heard of, which is SPC, statistical process control. And the technique was developed about 100 years ago in America by Schuhart. But I'd like to spend some time going through that, which you can see in front of you on the Excel sheet. And then I'm also going to do a small simulation example and show how important it is to actually understand the variation. So I'll come to that shortly. So the technique, there's a lot of myths surrounding the technique, and And what I'd like to think is that after today, that some of those myths that people have about SPC may be broken. So the technique can be used on any data set, but obviously you've got to be measuring the same thing. So we could use it to measure, for example, these are plastic rods. We could use this to measure the length of the plastic rods, and we could record the lengths of the plastic rods. We could use it to monitor cars on the road. So in a minute, how many cars go by in a minute, and we could monitor each minute how many cars have actually traveled past our house. So the way that the technique works, it's very important that the data is collected in time order. And so therefore, it's always possible to use this technique if you're in the process of collecting data, because you're obviously going to be collecting your data in time order. So if we have these plastic rods and we were measuring them and we were recording the lengths of the rods. So if I was to measure some rods and record them, I could record the data. Now, when the technique was first developed by Schuhart, he didn't have a computer and he used pieces of paper. So what I've got here is I've got this area here where I'm going to put my data. So if I was collecting the lengths of the rods and they were 200, and then the next one was 180, and the next one was, well, before we do that, if I only have two pieces of data and I wanted to understand the average, well, I could just take the average of the two pieces of data. And if I wanted to understand the variation in the data, obviously with two pieces of data, I could get a measure of variation. It wouldn't be particularly good, but I could get a measure of the level of variation. So if I kept collecting data from this process, and I collect 5 pieces of data, what I would then look to do is calculate and look at this data. So the first thing that we do when we get any data, and I know everybody's on mute, the first thing we do when we get any data is we'd want to draw a graph of the data. So here we see an example of our data plotted in time order. Now this already tells us quite a lot, because we can see that the average is, well, if we were to calculate the average, it would roughly be running through here. And the other thing we can also see from this is the amount of variation. And we could carry on collecting data from this process. And the question would be, how much collect before I actually average and the variation in the process. Now, if a process is relatively stable, like this one appears to be, then maybe we don't need to actually collect hundreds and hundreds of pieces of data, and that if we collected, say, 30 pieces of data, and the process had a fairly consistent pattern in it, why would we need to collect 31, 32, 33? We could still, the pattern really wouldn't change having collected just 30 or 30 pieces of data. But what Schuhart controlled, he looked at the data and he wanted to work out some rules for working out how much variation would be acceptable in the process. So he based on some work that had been done 100 years earlier than him on the empirical rule of data, he calculated that you could work out limits for a process, and in working out the limits for the process, you could use what he called his plus or minus 3 sigma limits. Now, bearing in mind he didn't have a lot of computing power at the time, just pen and paper, he devised a slightly different way of working out the amount of variation that exists within a set of data. And this measure was called the moving range. So when Shewhart he could have used this formula, but he said, well, this is a little bit too complicated for me. I'm going to use a formula where I imagine a walk along the data, and I move from the first data point to the second data point. And you can see that the change between 20, 200 and 180 is 20 units. Now, the thing about the moving range is the moving range will always be positive. It'll either be 0 or positive. And obviously, the smaller the moving range is, the less variation there is in the data. So he calculated this value, and I just need to drag that formula along. And what it basically does, the formula here, just works out the absolute difference between the adjacent pairs. Then Shewhart did some calculations on the to work out the average and the variation in the data, and he calculated the mean of the data. So he basically added all these values up, and he divided by the number of data points that there are. He then worked out what's called MR bar. Now, MR bar is just the average of the moving ranges. Having worked out the average of the moving ranges, he then needed to, what we then need to do is we then need to work out what's called our plus or minus 3 sigma limits. Now, the reason we pick plus or minus 3 sigma is because the empirical rule of data, which is on this slide here, you can see that the empirical rule of data is given by this. So if we apply the empirical rule of data, we see that at least 89% of data within plus or minus 3 sigmas. But with the development of modern computers, people have run around data spread within plus or minus 3 sigma, and you can see now that nearly always 99 to 100% of data is within plus or minus 3 sigma. Now, I can also show this graph here, which is a measure of, on this, the y-axis is kurtosis of the data, which is the peakiness, and on the x-axis is the skew squared. And here you can see all the different types of different distributions. You've got mounded distributions, J-shape, U-shape, and in this region here, you've got the Chebyshev and minimums. So if you had very skewed data with quite a large kurtosis, this is in this region where you'd get the 89% 3 sigma rule. So, but what we mostly see is data in these regions here, where you can see that the amount of data that's covered by 3 sigma is, even with really quite kurtose and skewed data, is still 98, 97.5. So given that most processes operate down in this field over here, we've got the 99% rule. So all we have to do is find a way of calculating from X bar and MR bar. We have to find a way of calculating the upper and lower control limits. Now, the work that was done 100 years ago, they discovered that MR bar was slightly bigger than sigma when calculated with this formula. So what we do to adjust for the fact that we're using MR bar here, we calculate using what I call SPC pi. So SPC pi is 2.66. So we make an adjustment to MR bar by dividing it by 1.128, and then if this wasn't 2.66 but was 3, and we divided that by 1.128, that would give us this formula here. So we have the average plus 2.66 times MR bar, and then for the lower limit we have the same average, but we take away 2.66 times MR bar. And if we do this, we end up with a chart that looks like this. So this is what's called an individuals chart. We can also plot the moving ranges as well, but because we've got individual values on here, we can actually see the amount of variation as well. So there are some interesting features about this chart. If all the data that we've collected lies within the upper and lower control limit, then we can say that the process is stable. And if a process is stable, we can then say it's predictable. So if it's predictable, it means that we can take these two control limits and the average, and we can extend them into the future, and then we can then use this chart to continue to monitor our process. And what we know, based on the empirical rule of data about the control limits, is that if it's stable and predictable, 99 times out of 100, or at least 99 times out of 100, we should expect to fall between these two limits. Now, as you can see from this, if we just worked on the average, we would be missing so much, because by tracking the movement in the data, it allows us to see how much variation we have. And obviously, over time, the process may start to drift, or the process may change as we do improvements. And again, we can use this type of graphic to track the process that we're interested in. Now, as I said, it works with continuous data. But as I also said, it also works with discrete events. So I might monitor the time between an event happening. And again, I can use this technique to do that. So rather than recording the lengths of the rods, I'd just be recording the discrete events, so the time between the discrete events. I may well go into a manufacturing process and work and see how long a component waits before it enters into a process. So if I just move out of the way, I've got my calculations behind, and what I can do is I can extend So what we have now is, because the data here it lies between the two limits, we can extend these into the future, and I could continue to monitor this process, and I would expect the rod length to be between these two numbers here, 152 and 250. And if I had a customer limit of 260 to 140, I could would be acceptable to those limits. Obviously, as I collect more data, these limits would become more refined, and then they would come closer together as I collect more and more data. But as a technique, it's a very powerful technique for just monitoring what's actually going on in a process, and then we can, with very simple maths, construct some limits for that process. If when we construct the limits we find the process is not stable because we have data points outside the limits, then this would be a point at which we would want to do some investigation into why this was happening. So what I've done now, so that's the basic principle. So I hope that's clear. And what I've now done is I've now created an example where I will go through this example. So what I've got is I've got a process where I have a system where the target time for the system is 55 minutes. And then I have two process steps. So what I've got is two process steps, and I've got two different scenarios. The first scenario is I have a process where it takes 20 minutes and the variation is 1. And the second process step is a 30-minute process with a variation of 1 unit. And then I have the same process, but I've increased the variation to 3 for both of the process steps. And as you can see, obviously the average for this is 50, the average for this is 50. So again, I hope this supports why you shouldn't just focus on the average. So if I can use Excel to generate some random numbers, and here I've collected sort of 30 random numbers about process number 1, and I've collected 30 random numbers about process number 2. I add them together, so that's that number there. I add these two numbers together, and then I calculate my upper and lower control limits for my process. I've also got an additional column at the end, which is working out how many times I go above 55, the time of 55. So what I can do is, if I've got formulas in it, and I can play with the formulas, and you can see that the control chart limits move for the process where I've got my sigma at 1. So I've done exactly the same thing for the process where I have a sigma of 3. So again, the average for both of these processes is pretty much the same, but the sigma, and you can see that the impact of having a sigma of 3 is that the control limits are much wider. Now you might be thinking, oh, well, that's good because sometimes I'll be much quicker. But yes, this is true, but there are other times when I will also be outside my specification limit of 55 minutes. So the problem of having too much variation, as we have in this example here, is yes, I can be quicker, but then how do I resource a process like this? Whereas with this process here, if I have a consistent level of variation, at least I know how much resource I would need for this type of process. Whereas this one here, I potentially, when I'm very much quicker, I would then have people standing around and I wouldn't know what to do with them. So invariably, too much variation would lead to me having more people in this process than in this process. And if I compare the two processes, which I've done here, I can see that my 5, I can, if by changing these, it makes it just makes the process jump, and you can see that you can run various scenarios around the process. And you can see that the variation. So I know that later on in the morning we're going to look at a much more complex system, but I hope this gives you a flavour that by just focusing on the average, as you can see, the blue lines are very much the same, but the picture that you see when you focus on the variation as well is one where you get the true picture. Now, there are obviously other statistics you can work out about data sets, skew and kurtosis being two of them, but you don't actually need to use them, because we know from all the work that's been done in the past around the empirical rule of data that the only two numbers we really need are, we need the mean to check where we are in relationship to our target, but more importantly than that, we also need to consider the variation. The variation is key to understanding how well our processes are going to perform. So when we look at simulation, people, well, for example, on a value stream map, people will focus on averages and how long things take to do on average, but they're actually missing the very important factor of how much variation there is. So the actual calculation of how to work out how big the variation is, as I showed before, can be done very simply by using the data that you've collected in time order, which is measuring the same thing. We then calculate the difference between the adjacent data sets, data points. We calculate the average for the moving range, and we then use these two calculations to work out what are effectively 3 sigma limits. But we use SPC pi, which is 2.66, to do the calculation. And as I say, when I teach this topic, this is all primary school maths, but it's amazing how little this technique's actually used to understand variation in systems and to understand whether a system's actually functioning as it should do. So in conclusion, sigma, 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 variation, variation, variation is very, very important. And the mean is also important, but unless we focus on the variation, we will not understand our systems. So I hope that's clear, and I think I've been a bit quicker, but there you go. I haven't any more to say. What I really wanted you to, what's important is that when we do the thing later on, is the variation in the system, because I only showed a very simple example, and obviously when we move to 50 or 60 machines in a process, and the variation becomes very, very important.
I don't know if you can see the question from Asinine.
I think the answer to that is, if you just use averages, you can draw a nice picture on a piece of paper. If you then have to start taking account of the variation, you need some dynamic model.
Okay. I think as well, Jonathan, it's probably something to do with how we are with regards to statistics, culturally in organisations. I think there's often a fear of statistics thinking it's very complicated.
Yeah, no, I would agree with that. But certainly when you show the control chart, when you show that type of control chart to people, and then you say to them, you can plot anything. So for example, if you play a sport, you can plot your scores. You can work out some limits for what you should expect to achieve. People start to understand the technique, and they start to realize, that, there's limitations to what they can and can't do. And the same is true of any system. It's understanding what the limitations of the system are. Because obviously normally that would be done on a piece of paper. And it doesn't have And then, for example, people draw histograms, but the point about a histogram is you lose all the time order in the data. This is the only technique that really takes you from, so here we've got the past, and then any data coming in here would be the present, and then we can then go through to the future. Very powerful.
There's one more from Pedro, Jonathan, about the order of the data, how the variability.
Well, the data will come because you're monitoring the process over time order. So that the order of the data, you've got to make sure it's in time order. Otherwise, it's not a control chart. So that's very important. The data's got to be in time order. So if you can't get it in time order, you really shouldn't use the SPC chart. But the limits change because of the order of the data. The important thing is when you're doing the SPC, when you're doing this, that the data's in time order. That's the important thing. The data must be in time order. And if you rearrange them and still get the same control limits, that's just pure coincidence. When I monitor my process here, it must be in time order.
Yeah, I think the question from Pedro's arising, and Jonathan, is he's probably thinking about the standard calculation, standard deviation. Yes, it would be the same.
That one, yeah.
But if you change the order, you're moving the range and show a different pattern.
Yes. So you don't need that formula. So for years and years, people have used that, but you don't need it. You just need the differences between the values. It's a fascinating topic once you get into it. But the main thing that you can do, if you can take away from this, is have a go at trying to develop a graph and then monitor it. And the more data you collect and the more you plot, the deeper your understanding of how to use the charts becomes. And then when you see that the variation in the process, you think, well, what can I do about that variation in the process? What can I do about this variation? Okay, thank you for listening.
Excellent. So I'll just skip through this, but the purpose of my presentation then will focus on the use of simulation, and this is, I think, a natural step after what Jonathan shared with us. So I think you'll get to see in a couple of slides why the subject of variation is so crucial to simulation, and why it is of such importance when we're trying to understand a manufacturing system or a logistics system. And then I think the rather more interesting part will be when we get to hands-on trying some examples and how something very simple can really give insight into a process. Before I start, my name is Erik Flores Garcia. I am a doctor in production innovation, and I work very much in the area of simulation with building digital twins, and specifically in the area of production logistics. I work at the Royal Institute of Technology in Sweden, and I am based in Södertälje, just in front of AstraZeneca, actually. As part of what we do, as research is concerned, as I was mentioning, a lot of what we work with has to do with production logistics in the area of simulation. So I would like to maybe begin by telling you a little bit about the objective of this course. And the idea behind this is to gain an understanding and competence on the use of one type of simulation, which is usually referred to as discrete event simulation. I will come back to this concept in a couple of slides and explain what it means and where can it be applied. But perhaps more importantly, the purpose of this webinar is to understand how is it that simulation may improve making decisions in industrial processes. I think if I may look back into the use of simulation at different manufacturing companies that I've been working with, this is usually a tool that many lean departments or production engineering departments or quality departments utilize. And this becomes an asset in addition to what many factories currently have. And as we will see, this is not to say that current tools must be discarded, but that instead simulation is a way of furthering your understanding. To begin with, I would like to maybe make a distinction between what we refer to as modeling and what we refer to as simulation. And so when we talk about modeling, we usually refer to as a representation of a system. And this is important to highlight because many times when we build a model, we cannot make an exact replica of a system. And so therefore it becomes crucial to focus on the essential aspects of the system that we try to represent. So therefore, a lot of the quality of the outcome depends really on the modeler, how people interpret a system and what becomes essential to represent. Very often, I would say almost certainly, we will need to discard certain information and really focus or narrow down on a limited number of questions that our model will be able to answer. Now, when we talk about the simulation, then we usually think of simulation as an imitation of a system. And this imitation is computer-based, although there are a number of examples in which we can maybe play games with physical objects that are representing a real-life system. And so with simulation, what we try to do is we try to experiment and very importantly, try to see the progress of a system over time. Now, why is it that simulation is useful? And there's a number of reasons for this. First of all, we are able to experiment without disrupting the real life process, be that in a factory or in banking or logistics, etc. We're able to test before we actually implement a solution. Many times when we wish to test something, we have a hypothesis of whether this may work or not. And so therefore, through simulation, our hypothesis can be confirmed or rejected. In addition to that, what we also can do with simulation is that we can experiment over time. So this means that we are not only able to test with one segment of data or with one group of data, but with changes in data and see the consequences of these changes. We can also work with the interaction of variables and test what-if scenarios. Well, what if we had this type of alternative as opposed to this other one? what if the demand suddenly increased? Or what if the demand suddenly decreased? What if we were to acquire additional resources? Or what if we had to reduce the resources? And very frequently, what we do with simulation, especially when it comes to logistics or production systems, is that we try to identify bottlenecks in a dynamic way. Now, as time has progressed, the importance of simulation has increased. Simulation as a tool supporting decisions is not new. It has been used since the 1940s. But as the needs of manufacturing have increased, so has the need for simulation tools. And I think that this is perhaps best represented in this graph in the sense that many of the products that we currently make are being increasingly customized. And in order to really achieve that, then it means that our production systems need to be flexible. And the degree of complexity that originates from that flexibility is difficult to comprehend if we are only basing our decisions on paper and pencil. So there is, with this, what I'm trying to say is that there is an increasing need for more sophisticated tools that can really help us understand the processes that we currently have in factories or any other type of systems. So many times the question that we get when we are trying to build a simulation model is, will it work? And this is, will the system work? Will the change in the factory work? Will this new idea that we have, will it work? And very frequently, the tools that we possess to support these decisions are, for example, value stream mapping, or perhaps there is an Excel chart, or some other tools such as spaghetti diagrams. And I think, as I pointed out a couple of slides ago, these are very useful tools, but perhaps a problem is that they are static in nature. And while being static, we can only provide an answer for a limited number of questions. And I will take an example, for instance, if this were to be our factory. Let's say that we identified a problem in this station, but this other station may be supplying to our problem area. And prior to that, we may have this other area in forming a link or a chain of value-adding processes that end up here. What we can see through simulation then is not only a focus on where the problem is occurring, but how the three elements are interacting and how they interact over time. So this creates all sorts of insight as far as knowing the flow of material that is occurring, the type of resources that we should allocate, or as it was pointed out in the last presentation, how variation is affecting the process. So then why focus on simulation? I would say that there's three reasons why it is important. One is the subject of variability. It happens every day. Unfortunately, as one of the comments in the chat described, the focus frequently is on the average, on the mean. And so then if that is the focus, then we are blind or seldom take into account the variability of our process. Another reason for using simulation, as I pointed out, is that, well, we're able to test how two different machines, how two different sets of processes interact. And finally, what we can also do is that we can predict effects over time. And I'll make a very quick example, and this will perhaps be our first our entry towards the software that we will be using in a couple of minutes. But let's consider a very simple example, and let's say that we have a breakthrough product that is this Rubik cube, and that management tells us with this thing we will take the company to a new level, and management tells us, well, I want 2 of these things per hour. And the manager comes to operations and says, well, can we make it? Can we really produce this 2 products every hour? And so then engineering says, like, yeah, sure. I think we can. We can probably do so in 10 minutes in each stage of the process. So then we should be able to meet the target. But the question is, will we be able? And I am very often surprised at that many times decisions such as the one that I am just putting on a PowerPoint slide in a very simplified way are based basically on averages, and that we seldom take into account other considerations, such as, for instance, the variability that our machines may have. While we may be able, for instance, to achieve, as in my example, a 10-minute machining process for every stage, we have a certain variation that is affecting our process. And perhaps this is intrinsic to the product design, or perhaps it's intrinsic to the type of technology that we possess, or to a number of things. Then, of course, there's also quality. I think seldom does any process achieve 100% quality, or if ever. And then we also have, of course, the failure of our machines, and that it takes time to repair them when they fail, and that repairing these machines may also imply a certain amount of variation there. So that being said, then maybe I can show you a quick example of And so then hopefully you see my screen right now, and you see the extensive software which we will be working with later today. And what I've made here is 3 machines represented in this figure. And if I run my process, what we will see is a raw material that is coming into machine, and this is being processed by the machine, and then it's moving on, and so on and so forth in 3 steps. Now, what you see at the end of the process is the total amount of products that we've made. This is a very simple process, and what I have done is that I am running 480 minutes, which would be equal to an 8-hour shift. I'll just speed it up so that we see our process. And what you're seeing at the moment is something that is basically flawless. We are executing with 10-minute processing time for each stage. There have been no defects, and there have been no breakdowns. So what we would expect then out of our 10-minute process at the end of a 480-minute shift would be 48 pieces. Of course, I have work in progress here, so we're about right. Now, what would happen then if my process were not flawless and it was in fact affected by both variation in my machining, variation in terms of quality, and variation in terms of breakdowns in the machines? So maybe we can take a quick look at what that would look like. Right. And so I'm executing basically the same process as we did before. And so now what you start to see when we have one of these green balls down in the below the machine is actually an accumulation of my products. So I'm not able really to reach the same margin or the same amount of products as I did before. So instead of having 48 or 46 of the products as I did when my process was flawless, what I have right now is a lower amount of products. And I think this is only to exemplify with in a very, very simple process. I want to highlight that how something as small as a variation can start to affect our outcome. Now, if I may go back then to my PowerPoint slide, and perhaps you remember the setup that I had. I was talking about 90% quality rate. Perhaps the variation here in my process is not that big, and so on. So with this, we begin to understand the effect that having a variation in our process may mean. Right, and so that being said, I want to then jump into the subject of discrete event simulation. And simulation in general is it's a huge universe out there, and we will only focus on one type, which is discrete event. So what does this really mean? What is a discrete system? Well, a discrete system is, we're focusing on a moment in time. We're analyzing a particular action that is occurring over time. And this is by far the most common type of systems that we have in both logistics and manufacturing. It is very similar, in fact, to what is done frequently in value stream map analysis. And what really becomes the subject matter of bottlenecks or identifying bottlenecks in a production system. So we could understand then really our discrete system as this moments in time in which we are analyzing a process. And it is through the tracking of these individual moments that we are able to comprehend how the system is behaving over time. And if you may remember then my opening slide talking about modeling and how our choices then really affect the outcome. Well, it turns out that we can really model many of today's systems with from a discrete event perspective. And so then there's basically four key elements that are involved in discrete event systems. One, we need to consider a progression of time. Two, we need to take into account activities or events that will consume time. And what I mean by this is that in the example that I presented with three machines, each of these machines were consuming a certain amount of time, which I assumed in the beginning to be that of 10 minutes. So this means then that there was an event occurring, this machine's machining the product, and that was time bound, and that it would be consuming a certain amount of time. A third element that is of importance is that of variability. And I would like to highlight this because this is what really makes the difference between a discrete event simulation model and, let's say, an analytic type of a solution in which we're relying perhaps only on multiplications or additions or etc. So most of the time, I would say, most of the times when we talk about the discrete event simulation model, then we're dealing with variability and with a stochastic system. And then there's also a certain element of randomness. Why is it that we would like to include randomness into our models? And the reason is that frequently we would like to see the effects of certain interactions for which we need to express them as either a probability or as a percentage or as a proportion that will affect our system. And to give an example of this, say for instance that we may have 100 different product types to make in our factory, and that this depend on, for example, a change in demand over different months. So then we would not like to have this demand fixed, but in fact to be closely representing how the factory behaves. Right. And perhaps this is best seen with an example. This concept of a discrete event system and how is it that we work with a discrete event simulation. So let's assume that this is our factory and that we have two processes that at some point will come and assemble a product together, and we will continue to add value to our product. So to begin with, perhaps what we need is a schedule of orders that we need to comply with and that we need to meet in our process. Of course, there's a need to consider a certain raw material consumption here. And as our raw material comes into our process, we will maybe have to add resources that will transform this raw material into something new. And we will continue to add value throughout the process. Perhaps, as I pointed out, at some point, these two products will become one. Maybe it's an assembly. And then perhaps at some point in our product, we will have a breakdown or a material shortage or a quality defect or a type of a problem that you may think of that frequently occurs every day in the factory floor, that affects the performance of whatever it is that we're trying to make. And then at some point, this issue at the factory floor will be fixed, and we will be able to continue to add value to our product. And so I think what I just described might apply to basically everything that we do in a factory. And this may be cars or medicines or food and beverage, paper, or warehousing. So perhaps what I want to really emphasize here is that taking into account the variability of our system and how this comes to affect different stages of our process is crucial to really understand whether we are able to perform the way that we're expected to perform. So question that is frequently asked is simulation a solution for all? And of course, it is not. There are certain areas or certain type of problems in which simulation is appropriate. For instance, if we are going to study or experiment the interaction of elements in a factory, if we are interested in seeing changes and their effects, their consequences, if we wish to verify an analytical solution, if we've already worked out in paper and pencil, in a value stream map, in an Excel chart, and we are not able to take it further, we already have an idea that what might be the solution, but we, for whatever reason, we would want to verify this. Perhaps it will become a very expensive investment. Then it certainly makes sense to do this with a simulation. Very frequently, we utilize simulation for training purposes, in the sense that either for production engineers or for operators, so that they become familiar with making the right choice and understanding the consequences of a choice. And also to determine the requirements of a process. As you will start to see when we come to our hands-on example, one of the key aspects of simulation is that we're able to test what are the limits of our system. And so therefore, this can help us not overcommit or underperform. However, there's certain circumstances in which simulation is not appropriate. And I want to point out, number one, simulation is time-consuming. Most simulation models will require months to be built. And this is not because actually programming the model or putting elements, as we will, into a model is time-consuming, but because it is very frequently associated to the collection of data. And as of today, collecting data is both expensive and many times we need to clean the data. So if we were able to answer a question without walking into a simulation model, this is probably a good way. That takes me to the second point, in which analytical solutions are perfectly fine. They've worked in operations management for a really long time, and they will continue to work into the future. But if we are interested in taking into account or modeling a stochastic system or seeing the interactions of elements and so on, then perhaps we should move forward with simulation. if we're able to perform direct experiments, this is certainly something that you would like to do. As I pointed out a number of times so far, whenever we walked into a simulation, we're making assumptions or simplifications that, of course, the more of these that we make, the further away we are from reality. And so if time and budget are available to perform direct experiments and we know what we're looking for, then this is certainly something to be considered. Many times, as I've said, simulation models are expensive, they're time consuming. And if we are not able to afford the entire process of executing a simulation model, then perhaps it's best not to do so. What do I mean by that? That just because we're adopting a simulation tool, it doesn't mean that the result will be right. For a simulation model to be right, we need to verify and validate. We really need to make sure that it's working accordingly and appropriately, and that takes time. So if this is not done, if the simulation model is not validated or verified, we run the risk of making decisions based on false data. And this, of course, becomes very risky. Yep. So this is also very, very much associated to the lack of resources at the time. That being said, this will conclude the first part of my presentation, and I would like to ask if there are any questions. And if so, just please raise your hand or type it in the chat, and I would be very happy to answer them.
All right, I'll propose that we go for a break. So just to check, are there any questions? If not, we will break now until 10:30, and then we'll start again with the next section from Erik.
Great. So what we will do for this second half is that we will be playing around a little bit with extent sim. And if you were, hopefully you have the demo version or some sort of license that you can follow along. And if not, I think this will still be of use to you. There are a number of softwares available that basically do the exact same as Extent Sim. And I will begin maybe by perhaps showing some of the more advanced examples that are available and included in the package. So if you were to go to this, for instance, this as discrete event model, and we take a look, for instance, into an example on the manufacturing of electronics. And if you've done this right, what we see is something like what I have here. Now, this is a very simple process in which we have a number of orders that are arriving and a series of steps in our process as we're trying to manufacture a circuit board. I'll run my simulation, and what you will see is this circuit board being processed. So then there's some sort of soldering, components are placed, then the cards are baked in an oven. And as you can see, there's an accumulation of these. They're baked as a batch. And then finally, there's an inspection. And as part of the inspection, some may be defective, while others are good to go. Now, what we have in this process, as you can see, my flow of material has stopped. And what we have in this process is that every now and then there is quality defects, or there may be problems at any stage of the process. And as these problems are being fixed, then we see a lag in the flow of our material. Now, this being a very simple model, perhaps it would be quite easy to grasp in a real-life factory. But more often than not, processes in factories are not exactly next to each other. More often than not, this process may be on one end of a building as opposed to this other one, while these two may be perhaps in another facility or maybe even in another country. So really understanding the flow of what is happening is difficult to comprehend if we do not possess a holistic perspective, such as the one that we could potentially generate with a simulation model. I will stop this for a second, but I think you begin to understand how this works. Now, an interesting part of simulation is that we can interact with the models and test what-if scenarios. Now, in this process, in this model that you are seeing, the issue or the bottleneck is the number of inspectors that we have for our circuit boards. And so since we know this from the beginning, our model has been specifically designed to test this variable. On the upper right, left-hand corner, you see number of inspectors. And if you click here, you may select the number of inspectors that we can place at this stage. And of course, if they were able to work in parallel, we would naturally think that having an increased number of inspectors would probably help with the flow, as opposed to having a reduced number of inspectors. Yeah, I mean, that is basically correct. But I also would like for you to notice that above each of the processes, there is a label saying utilization. So what we're tracking, other than the number of products that we've completed, is also the utilization of each step of the process. I will run my simulation again, and I want for you to know the utilization when we have one inspector as opposed to the other extreme when we select a choice of 4. So I'll just quickly speed this up so that we are able to see our process. Right. So that, as you're able to tell, then our bottleneck operation is the inspection. And if you've been tracking this label from the beginning, the utilization has been increasingly on an upward trend, while these other processes are rather low compared to this one. Right. So now let's go to the other extreme and let's test 4 inspectors as opposed to 1. The exact same conditions, but our variable of interest has now changed. And as we wait for the results to come out, I would like to highlight that this is one of the desirable elements of simulation, in that we may be able to test the exact same model, so I think if you've been following here the animation, you would probably agree with me that this makes for a much even flow of materials. At least they're speeding through as opposed to what we had prior. And you can also tell that there's a difference in the utilization of our equipment here. So then the question is, what is the best option? And very often when we deal with simulation, what we wish to highlight is the trade-off that exists between the available options. And while we have been able to achieve very even flow, this of course may come at a cost of having an increased number of operators or of inspectors. And so then the answer to this question, what is the best option, needs to be presented in a way in which we are able to compare this trade-off between the cost of our operators or the inspectors as opposed to the throughput of our material or our products and any sort of work in progress that we may have. Let's take a look at another example. And so if you're able to, if we go into discrete event modeling, and then we go into service of a bank. And you should get something like this. Now, this is a similar situation in that we may have a number of individuals going into the bank, and the reasons why they come into the bank is that they may wish to discuss certain things at customer service, in some cases with managers. Sometimes they withdraw money or they deposit money, or sometimes they ask for loans. And depending on the time of the day and these options of services provided by the bank, the amount of time that each of these individuals spends in the bank varies. So of course, us as owners of the bank would like to see our resources being utilized and that we are giving the right service to our customers. If we were to reduce our resources, what would perhaps happen is that we would maybe have an accumulation of customers at a certain time of the day. And it is likely that if a customer sees that there's a very long queue, the customer will probably walk away, come some other day, or etc. I will just speed this up And what we are able to see here is we have maybe no accumulation of customers. So that's something that is desirable. But on the other hand, then we see here the utilization of our resources, that perhaps maybe customer service agents, which are currently 2, perhaps we could say service our customers with maybe one agent there. Just to make an extreme case, as I did before, instead of having 4 tellers, I will choose an option 1, and I will run the simulation and see what we have as a result. So then, of course, what you see is an extreme case in which we are, yes, on the one hand, utilizing all the time of our resources here, but then probably very unhappy customers. So then again, with models as simple as this one, then what we can test is what if scenarios, and they're answering questions for which the model is specifically built for. I really want to underscore this point in that we always build simulation models that are meant for specific questions. And whenever there is a need to answer additional questions that the model will for, this requires additional time and effort. Great. And then if you wish, and there's time, then there's other models that are available. Some are 3D, and so then you can just play around with this for our presentation. But then maybe what we could do, and I propose, is that we build our first model. So if you could click here on New Model Worksheet, this blank page that I have up here in the corner. You will have something like this, not much to look at. And then what we will do next is that we will go to the library option, and we will select Item and open library window. Now, if you've done this right, you will have a menu with different items to the right of your screen. Now, the way that extend-sim works is that there is very little programming involved, unlike other simulation software. And extend-sim works as a drag and drop type of a software in which we connect elements, and in the way we connect elements, then we are able to produce certain outcomes. That being said, then the first thing that we will do is to drag and drop this icon that says executive and has a clock as a figure. So if you've done this right, then you should have this executive block in the upper left-hand corner of your screen. Now, if you remember from the slides that we had before our break, I talked about discrete event models as being time-bound. And what this icon does, it will keep track of all time that is occurring in our model. And it will coordinate all sorts of activities that are time-bound. Now, that being said, maybe what would be appropriate to do is perhaps adjust the time span in which we would like to execute our simulation model. In order to do that, I will go into this option that says Run, and then to Simulation Setup. You should get a menu such as this one. And what this does is that it specifies the time that our simulation will run. Now, a unique characteristic of simulation is that we can compress or extend time as we please. So, for instance, we would be able to run a year worth of data in perhaps some minutes or hours, as opposed to a one-to-one proportion in real life. So there would be no need, in fact, of running a year of simulation in a year. And we could probably do this in some minutes or hours. That being said, then maybe let's type 480 in here as an end time, thinking that perhaps we would like to work with 8 hours and 60 minutes, meaning a shift. And then you will have a certain time unit, so we need to specify what is it that we mean by 480. And I will say minutes. So then I will just click on OK. The next thing that we will do then is that we will begin to drag and drop certain elements that will represent the exact same example that I showed prior to our break. So we will have 3 machine groups, or 3 different machines, and they will be connected one after the other, with the purpose of making a part every 10 minutes. So if you could drag and drop this item at the top of your item library, that is called activity. And we can do 3 of these as such. We'll also include an item that is called create. So we drag and drop our create block. And finally, what we will do is that we will drag and drop the exit block. Okay, so then what does this really mean? Whenever we have a discrete event simulation model, well, we need something that is starting or that generates the products, services, orders that our system will work with. And at some point, we will also need an item that is registering the total number of products, services, items that we have been able to produce or service during a certain amount of time. So what the create block does is that it will create our raw material, orders, products, customers, and our exit block will be registering the products that we are manufacturing or the customers that we have serviced. What our activity block does is then that it will consume time out of a process, in the understanding that perhaps this can work as a machine, for example, in which we receive a product, and after a certain amount of time of processing this product, we're able to produce an output or a different, to add value to our product. I'll connect these elements by placing my cursor on the right-hand side corner of the create block. And if you've done this right, you can probably notice that my cursor is changing form. So if I click and drag, you will see a line that is extending, originating from my block and to wherever I want to place it. Now, I want you to notice that if I were to place it on the left-hand side of my activity block, then this line becomes bold. If you drop then, whoops, sorry, as such, then you will make a connection between these two elements. And we will do the same over here. And the same over here. Like that. Now, if you've made a mistake, or if it happened as it did to me, like this, you can delete the connection by double-clicking on this link. And doing so will highlight the connection, and then we are able to delete it. Right. You're also able to take one of these items with the left button on your mouse, and then just maybe place it in whichever order you wish to place it. You also select any item and move it with your cursor. Great. So what we have at this moment in time is that we will be generating, or we will have raw material coming into our factory, and we will have 3 machines of equal kind processing our product in 10 minutes each, and then delivering this product at the end of the line. Right, just to maybe easier for us, we will look into each of these items to really understand what is happening here. So if I were to click, to double click on the create item, you would be seeing an option such as this. Now, if you may remember, with our create block, what we do is that we are able to generate products or services or whatever it is that we require in our system. We are able to create these items in a number of ways. We could do so randomly, or by a certain schedule, or infinitely. So for the time being, we will select to create this item randomly. And there's a number of options available. If you were to click here, where we have our list of distributions, we're able to see a wide range of options. So I'll just leave this as an exponential. Another option that we can play around with is the animation. So if I click on this tab, block animation. Oh, sorry, item animation. So if you click on item animation, then you're able to change the elements in your animation. By default, we get this green ball. But then if you click here, you would be able to select any of these options. So for the time being, I will just select maybe, let's say, an engine. Right. I will double click then on my activity block. And if you've done this correctly, a menu such as this one should open up. Now, what this activity block does is that it consumes time in the form of work being performed or an activity being realized. We can do this through a constant value, or we can also use a certain type of a distribution, different options available. For the time being, we will select a constant and we will leave this constant as 10 minutes. Another option that we can we start to include many elements into our simulation model is that we can identify our elements with a name. So in my case, if you go to this square on the left hand side of the screen, you're able to label your activity block or whatever block that may be. So I have just typed machine 1. And if I click on OK, you will see that the label machine 1 now appears underneath my activity block. I will double click again on my activity block and I will show you other useful features that are available to us here. So you have a number of options above, or folders, and I will click on this one that says results. Right. So if you've selected results, now what we see is a format in which we can capture the performance of our activity block. So what this really means then is that we would be able to track the performance of our machine throughout the duration of a simulation. We would be able to know the length of time that this machine has worked, if there has been a certain waiting time, if the machine has been off shift, or if it has been blocked, meaning that it had the potential to perform work, but for whatever reason, we couldn't pass on a product to the next stage of the process. So then this information is summarized here in the activity state statistics. So we are able to know how busy this machine was, if the machine was idle, meaning it was able to perform work, but no products came, and so therefore it stood idle. If the machine was blocked, meaning that it had the potential to perform work, but for whatever reason, the machine was not able to pass on the product. Perhaps there was a bottleneck or a machine failure. Or if there was a shutdown in the machine, meaning that perhaps there was a quality defect or a breakdown in this machine, and then we know what happened there. Right. So now let's continue making some adjustments here so that our process looks just like the one that we described. 3 machines with 10 minutes processing time each. So therefore, I will double click on this second option, second activity block. And I will change my delay from 1 minute to 10. And I will also label this as machine 2. Right. And finally, the same thing with machine 3. So 10 minutes and machine 3. Excellent. There's an additional element that we will include into our simulation. And this item is called a queue. So if you go into the library, the items are ordered alphabetically. So you should find the queue somewhere at the bottom. So I will drag and drop the queue item, and I will place it as such. So if you've done this correctly, your queue item should appear here. And if you have missed and misplaced the queue somewhere here, we are always able to select and drag with our mouse and delete the connector. Right. So what exactly is a queue? A queue works as a buffer. So in the event that we have a bottleneck in our system, in this queue, we would be able to accumulate the material. If this option were not available, then it is very likely that it would lead to a breakdown of this simulation model, in the sense that we would not be able to place material anywhere. And by having a queue, then we have a storage, so to speak, where to place the items that we are not able to process. So if you double click on the queue item, you'll see that there's a number of options available to us. We can work it as a first in, first out, or last in, first out, or have some sort of priorities here. But for the time being, we will work on the assumption that we operate on a first in, first out basis. If you were to click on the results, we can also tell a number of interesting things here. We will be able to track the length of our queue, the wait time of each of the items in the queue, the arrivals, and how many items have left our queue. And we are able to do that by tracking what is currently in the queue, its average or the maximum. Right. So let's make a first test. This is already a working simulation model. What remains to be done then is to run our model. In order to run our model, there's in truth two options. We can run our model with an animation on or off. To run our model with an animation on, I'd like for you to refer to these options that are above your screen. And if you see an icon with a bouncing ball, and if you click on this, you see the icon activated. And if I click on it again, I see it with a cross on it. That means that the animation is off. And when I see the green ball bouncing, it means that the animation is on. So let's leave these on. And then this triangle that looks like a play option. So if I click on this, then I will run my simulation model. So let's go ahead and do that. And what we see then is our process. We see our engines coming in, our machines processing the parts. And we have our first working simulation model. I will stop the simulation by clicking on the S icon that I have here on top of my screen. When doing so, I will be prompted, the simulation will stop if you click the stop button. It will continue if you click the continue button. So yes, indeed, I want to stop. Excellent. Now, you could probably tell that I had an accumulation of material here, 73 items, and only 6 have come out. Now, a reason for that is that we are creating items at a faster pace than what we are processing. Now, we had agreed that my process would probably take 10 minutes each. So if I click here, and if I go to my Create tab, you can just click on this one. You can see that, well, we're creating items randomly in minutes, every minute as a mean. I will simplify my process here by creating items by schedule. And I will, if you've done this right, if you've selected creating items by schedule, we'll get a table like this one. Now, if we read through our table, we see that the create time for my item will be time 0. This means that as soon as we run our simulation, there will be 1 item being created. I would, of course, be able to change this item value or the quantity to whatever we would like. Maybe it's 20 or 2,000 or whatever number you can think of. So that's the number of items that will that my simulation model will begin with. I will go back to an option of 1, as it is 1 at a time that I am creating. But I would like to repeat this schedule, and I would like for my process to work or to process one engine every 10 minutes. So therefore, I will click on this option that says repeat the schedule every, and then I will select 10 minutes. Excellent. So then I will run my simulation model again. And as my model is running, what I can see is that I no longer have an accumulation of material there. And the reason for that being is that every step of our process is currently 10 minutes. I am generating engines every 10 minutes. Every 10 minutes, we have a new engine coming in. Every 10 minutes, we're processing 1 engine in machine 1 and the same in machine 2 and machine 3. If I go up here, you will, next to your bouncing ball, you see a button with a green rabbit and with a tortoise next to it. If I were to click on the rabbit, this would accelerate our simulation. And if I click on the tortoise, it would slow down our simulation. So you can toggle between these two options, and I think it's usually wise to try it out at different speeds to better understand what is going on. As we are working with a very simple process, then it's quite straightforward, but this is not the case, of course, if we are talking about several machines or several items. I will stop my simulation model, and I will include an element to track how the performance of my system. So if I go to my item library, you'll probably notice that there is a toggle button here with the title item. So if you click on this, there are different options available, and we will select the plotter option. And now we will select a discrete event plotter. So I'll drag and drop that here. Now, what we're about to do is that I would like to know how many items am I processing over time, as opposed to the items that are waiting in queue. And so in order to do that, then if you've noticed on my exit block, to the right-hand side, if I put my cursor on top of this item, I get a label that says the number of exits. So it's 43. Great. So if I click here and extend without dropping the button, I'll get this line. And if I place it on my plotter, I get this bold line, meaning that I have a connector, or a connection has been established between the two elements. So if I drop, then I can see that indeed there is now a connection established between the both of them. I will now run my simulation model. And I will take my animation off. And if you've done that, you will probably, if you have your audio on, you'll probably listen to a pling. That means that our simulation has stopped running. You can see that by the increased number of products that we have here in our exit block. Now, if you double click on your plotter, we get this chart in which we have the time in which we're running our simulation model. So from 0 to 480 minutes. And on the y-axis, we have the products that we've manufactured. So we've manufactured 46 products, and that is exactly what we have here in the chart. Great. Now, we would also be able to track how many items are in the queue. So in order to do that, we can place our cursor on the right-hand side, on the bottom of the right-hand side. You should see an L signal. That means that by connecting this element, we will be able to know the queue length of our process. So if you click here, you drag onto the plotter, make a bold line, and releasing, then you have a connector. And so if I were to run my simulation model again, what I have is, it may look like the same graph, but in fact it is not. There is a red line here at the 0. And so that really means is that we have no accumulation of material. And of course, that is straightforward, as we are creating engines every 10 minutes without variation, and we're processing engines every 10 minutes without variation. Now, what would happen if we were to change to the creation of items with a certain amount of variation? So if we were to double click on our create block, and we have this option. So now instead of saying create items by schedule, items like this, I'll just go with my exponential distribution, and I will select a mean of 10. So if we've done this right, I will click my animation on so that we can see what is happening over time. And I will speed it up just a bit. So indeed, we have a certain accumulation of material in our queue every now and then, which is according to the variation that we have in our create block, corresponding to that of the exponential distribution with a mean of 10. I'll take my animation off, and then I will double click on my plotter. Now, if you've done this correctly, you see a different graph from the one that we saw earlier. What you see in this blue trace is the number of items that we're making. Now, if you remember, the last time that we opened this plotter, we were making 48 items, and now we're only able to make, previously we made 48, and now we're about 40. Yeah, okay, 38. But in addition to that, we have this red trace that corresponds to the length of the queue that we have in our system. So since we have variation, this no longer is at 0, but is changing accordingly. Now, if we were to click with our plotter still on the screen, and if we were to click on running our simulation model, we will see a change in our graph. And you may be wondering, why is it that every time that we run our simulation, we see a different result? Well, the reason for that is that every time that we run our simulation model, we're executing our simulation model with our exponential distribution. And we are acquiring basically data that is being generated by the exponential distribution. So it's really never constant. You may think that, well, what's the purpose of this then? How do I know if this is correct? How do I know if there is the right answer, if indeed there is one? Well, this takes to maybe one of the first important takeaways of a simulation, in that we do not run a simulation model once, but what we would like to to take out of our simulation model is run a number of times. And depending on the conditions in which we run our simulation model, the number of times and the length of our run will change. But the general understanding is that we would need a number of samples and then run a statistical analysis on these results to determine whether our system is behaving the way that we would like it to behave, or to indeed determine if our hypothesis is correct or not. Great. So far, do I have any questions?
Erik, there was a couple of questions in the chat. I think there was one from Pedro, was around the use of the exponential,
Right.
because it's a pass-on process.
Yeah. So, I mean, as I said, this was only with the purpose of exemplifying the variation, but we were in fact able to select a number of options that are available to us.
Okay, and there was another one around, are we assuming throughout the simulation there was no correlation between the processes at machines 1, 2, and 3? And could you do something different?
Yeah, excellent question. Yes, indeed, that is what we are assuming. Of course, many times this is not the case, and what we are doing in one machine is affecting the next step of the process. It can be done, and I will just unplug my plotter here. So if you see my activity block here, there's a triangle that is pointing downwards. So I'll just place my cursor on top of the triangle and then drag. Then what I have here is a number of options that are available, in which these options are affecting the behavior of my activity block. And then what we would be able to do is place a number of maybe equations or correlations that would affect the way that my activity block behaves. That may be dependent on how the prior machine is behaving, or for that matter, perhaps a parallel process or a process that is supplying to this group of machines. So yes, good question. This in fact can be done.
Okay, and there's another question, Erik. There's one around, can you explain the differences in discrete event simulation versus system dynamics, and when would you use each method?
Right. Good question. So when we talk about system dynamics, we are usually trying to establish a relation between larger elements if we're talking about logistics in a supply chain. So take, for example, if we would like to see how maybe a supplier on one end of the world is affecting another one in the UK. When we talk about discrete event simulation, what we are interested in is compressing or extending time in particular events that occur in the system that we're trying to understand. So for instance, in this example that I'm showing right now, we would like to investigate the behavior of a number of machines or processors or activities within a time range. So whenever we have a situation in which we are replicating a system in discrete moments in time, then discrete event simulation would be the option. But if we are trying to maybe establish the dynamic behavior of events, then discrete event simulation may not be the option. We would need to look into the type of problem. But perhaps a systems dynamic approach would be more suitable.
Does that answer the question, David? Okay, Erik, I think there's someone's got the hand up. I can't see who that is. I don't know if you can see it from your end.
Sure. Where can I need
the hand's gone down now, so maybe someone that is asking the questions.
Yeah, great. And so then maybe what I think another important aspect that we can look into to start with when it comes to simulation or discrete event simulation is that we can provide attributes to our products or items, and these attributes will determine the behavior of products in a system. What do I mean by that? Let's take the example that I just showed with the animation on, in which I have an engine that is passing through the process. Very often, we deal not with one item or one type of product in our factories, but with a number of items or products in our factories. Or maybe it's also materials or supplies that we deal with. For instance, packaging. Maybe the product is the same, but the packaging for the product changes depending on the market that we have. And so maybe there's certain instructions that need to be sent to a type of market as opposed to another one. So how is it that we would be able to make these variations, if you will, in our simulation model? And so then to do so, I will just assume that we have maybe one engine type to begin with, but depending on how we machine that engine, we will maybe take two different paths, and eventually this will change into two different engines. And again, this is just an example, but this could be anything else. So I will delete this connector, and I will just copy and paste to have the exact same values that I have on top as I have below. I'll just delete my plotter as well. And what I will do next is that I will go to my library and my item library. And I will select an option that says select item out. So I'll drag and drop, and you should have a connector such as this one, an item such as this one. Right. So I'll connect this in such a way and so what we are doing here is that we are dividing our flow of material in two different streams. Now, there's a number of ways in which we could divide our flow of material. And perhaps to begin with, we will think that, well, 50% of our material goes on the upper stream and 50% of our material goes into the lower stream. And so then how do we determine that? If we double click on our select item out, we get this set of options. To begin with, we have a random option, this meaning that we will follow a certain proportion or certain probability, in which our flow is divided. And so if I wanted a 50-50% probability, then I would leave it as is. But then let's maybe think that the upper flow gets 60% of the engines and the lower flow gets 40% of my engines. And so if I've done this right, I just click on OK. And I will run my model with my animation on. So then I will just speed it up. And eventually you will see my upper flow with a larger number of items than my lower flow, which will correspond, of course, to the proportion that we've selected. Right. So that's one of the possibilities that we have. Another possibility that we have here is that we may select whether the flow will be the upper one or the lower one based on a sequence. And what this really means is that we will first look if there is capacity available on top. And if so, then our item will be directed here, our engine. And if not, then our item will be directed below. In such a way. Right. Now, the third option that is available to us will depend on the type of product that we make. And so for this, then, we need to determine or establish an attribute for our engines. I need to make a bit of a space here in my model. So drag this left-hand side, and I will include an item called set. So I'll just drag and drop and place it somewhere here so that this is connected. As I have said, the purpose of this item will be to brand or establish an attribute to the engines that pass through this block. So in this case, I will say that the engines that are of type A will go to the upper flow, and the engines that are of type B will go to the lower flow. So then if I double click here in my set item, I am able to establish a property for the engines that are passing through. So I will select new string attribute, and really what this means, new string attribute, is that we are able to type a word or a series of characters that will basically become the name of our attribute. So in this case, I will say engine type. And then maybe I will say engine. So click on OK. And now what I would like to do is establish what proportion of my items correspond to engine A or engine B. To do so, I will go to my library and I will go to the value library. And so then you're able to tell if you're in the value library not only by the label here, but the color of the icons, which are yellow. And then I will go to random number because I want to make a distribution that will determine the type of engine that I'm working with. So just connect these two as such. Now we'll double click on my random number. You will get this menu here. And so I would like to make an empirical table. And what this really means is that we are able to establish a probability for a number of elements in our system. And since we've established that we have two engine types, I am only interested in two elements. And so then I select the two. Should get something like this. And since we're already connected to our set block, we're able to toggle between our engine A and our engine B. And now we can establish what probability of engines type A do we have, and maybe let's say that we have 80%. Our engines are type A, and 20% of our engines are type B. Notice then this add up to 1, of course. And anything other than 1, you will get this reminder that there is still a proportion to be established here, a proportion of our 100%. Great. Right. Okay, great. So then we've said that to begin with, we have blanks, so to speak. There's really no distinction between the type of engine, but that some of them will become type A's and some of them will become type B's. We've also established that 80% of those engines will become type A's and only 20% will become type B's. Great. So we've already established the proportion that we want. Now we need to establish how is it that the engine types will be distributed. And to do so, we will click on our select item out icon. And you may remember that we had a sequential option. We would like to change it to a property. And this property is determined by our engine type. So if I click on display string attributes in table, now I would be able to say that engine type A, go to, and engine type B. And so then we can determine which output would go to which. And so if we've done this right, select output 0, it corresponds to the upper exit, and select output 1 corresponds to lower exit. Right. And if we run our model, we can see that our engine types A are going to the top, as are most of the engines. And eventually we will get an engine type B going to the lower flow. Right. I think, Omar, correct me if I'm wrong, but I think we have 15 minutes, right?
Yes, sir. It'll be a good time for break now.
Right.
And then we'll come back for more broad discussion and any final Q&A from the guys.
Perfect.
Okay. I think there was one question, Erik, that Pedro couldn't find the plotter.
Right, okay.
In the version of D that he was looking at.
Yeah, so I can do that. So to find the plotter, you go into this library, and then you click and select plotter. Now, there's a number of plotters available, and this really depends on what is it that you're modeling an extents in, but the one that we're currently concerned with is discrete event plotter. So you could just drag and drop that, and it would look something like this.
I'm not sure if we have the same software, because the PDF I opened up, it said as of extensum 10, the plotter library is in legacy status, replaced by the chart library. I was able to find the chart library, but I didn't see the plotter library.
Yeah, sorry. I forgot to mention to you, Erik, that we are using the 10 now, so it's a bit different visuals on it, and it is well, as you said, I can show my screen if you want.
Absolutely.
Just to show how it looks like in the 10. And these are the different libraries we have. So the chart one is the one about the plotters.
Yeah. So I got a question, Omar, about it looks like a fantastic tool. Obviously, there's a lot in it. We have an application in Capel in terms of the QC laboratory, so we could simulate and figure out as we expand the site, what we need in terms of capacity to get the throughput that we're going to need. My question was, how does the licensing process work, and what kind of support is on offer in terms of getting started and getting people, to become practitioners with this application?
Okay. So Mark, we're gonna pick that up in a session that we have internally later today. But I can share more on that.
Okay. Thank you.
Any other questions?
No, just on that question before around the plotter, you can open up and load the legacy library to load that plotter function, but I'll just tell you that it's not supported anymore.
Is that a question for me, Ian?
No, that was a question. That was just responding to the fact that we couldn't see the plotter in the default library, but you can open it up and load the legacy library for the plotter. That's just what I discovered playing around.
Right. Yeah.
It sounds like there aren't any more additional questions. So I think if there aren't any more questions, I'll just open it up. Or maybe any final questions directed for Jonathan in the presentation he did this morning.
Okay, so then I see that in the chat there's a question and it says, can you output results into a report? Yes, that is possible. You can export your results to Excel, for instance, and then through Excel, handle data as in whichever way you wish. So that is an option.
Okay, Luz, I don't think there are any more questions. I think we could probably draw the workshop to a close earlier if there aren't any final questions from the attendees. So I'd just like to say thanks to Erik from KTH University and to Jonathan from the QS section for the RSS for the time today and taking us through those couple of really good presentations and instructions around the use of data in terms of understanding variability and building simulations and optimizing supply chains. Okay, so on that note, I think we can end the call. Thanks, everyone.
Thank you.
Thanks so much.